Alright, we're going to do an optimization problem within designing a box. So an open top box is to be made by cutting small congruent squares from the corners of a 12 by 12 inch sheet of tin and bending up the sides. How large should the squares cut from the corners be made so that the box holds as much as possible? Well, right here on the left is a picture of the 12 by 12 sheet of tin, and as you can see here that there's been a little square cut out of each corner. The sides are going to be folded up like shown over here on this right hand side, where it'll make a box with an open top. So we're going to call these corners X by X. We know our sheet is 12 by 12, and we're going to figure out what is how large should the squares be cut so that you can make the box hold as much as possible. So we're looking for the maximum amount this box can hold. So we're looking at the maximum amount of volume that this box can hold. Alright, so we're looking at when this box gets folded. So I'm going to kind of write on this square right here. So if I fold this box right here, let me erase what I just made here. If I fold it here, cut the corners out and fold it right here, fold it right here, fold it here, here. Do you see where there's going to be a box with those corners cut out? This is a kind of a good picture. And by doing that, the inside of the actual bottom of my new box is going to be 12 minus this x and this x, so it's 2x. And since this is a 12 by 12, this happens to be the same. So that's also going to be 12 minus 2x. So if we're looking for the maximum amount this box can hold, like I said, we're talking about the maximum amount of volume. So I know the volume of this shape is going to be length times width times height. And we know that when we fold it up, as you can see this picture right here, how high our box is going to be x high. So that's our height. So I'm going to say that we'll do that first, times both of those sides, because it's a square piece of tin. And we don't have to have a constraint equation because this is what we need, and the constraint has already been written into the problem. So our numbers reflect the constraint of the 12 by 12 sheet of tin. So now I'm going to do the volume. I'm going to multiply these two first, and then I'm going to multiply them all by x. So I have 144x minus 48x squared plus 4x cubed when I get all done. Alright, so I multiplied those two parentheses first and then multiplied them all by x. Then I'm going to do the first derivative, put it equal to 0 because I want to see what it's going to be. So v prime is going to be 144. Excuse me. Yes, it's going to be 144, but I'm going to kind of write this around. I'm going to do this first so it's in order. So it'll be 12x squared. Then it'll be minus, I'm kind of doing this a little bit backwards so it looks nice when I'm done, 96x, and then plus 144. I was going to do it the other way, but then we'd have to switch it around. We're going to put that equal to 0. Now in order to solve for x, I'm going to first of all, my pen is being very touchy today, I'm sorry, I'm going to factor out a 12. And when I do, I have x squared minus 8x plus 12 equals 0. And then I'm going to do the big T here. 12 will never equal 0, but we're going to try factoring this. And when I do, I get x minus 6 and x minus 2 equals 0. And then we're going to put both those pieces equal to 0. So x minus 6 equals 0. X is going to equal 6. X minus 2 equals 0, so x equals 2. Now this is a good problem to show you where I came up with two x's and I'm looking for the max volume. Before I even look at this little graph on the right that I have here, let's just look at our picture here. I'm thinking the answer is 2 because if I had x be 6, if the whole side is 12, so right here we're looking at this, let me change the color here, this whole side of my box is 12. If I cut out a square of 6, that's halfway, that's like a folder. So it looks like the 6 is going to give us the minimum amount. Alright, so I'm thinking x equals 2 might be my answer. because it looks more reasonable. But here I graph this, and it's in quadrant 1. So here we just found x is going to be 2. So we just found right here x is 2, and we found x is 6. Well, we just kind of looked at our picture and just by common sense said, okay, if x was 6, it looks like the volume would be 0, which it is because it's a folder, and that doesn't look like the right answer. So 2 looks like the max, and again, we're looking at, it's a cubic equation, but when I take the first derivative of it, it's squared, and you can see where here it looks like this is going to be our max volume when x is 2. So let's check this out using the v prime bar to see if really what we're thinking is correct. So let's do a v prime bar right here to see how it would look. So I'm going to tell you right now, for a cubic equation, it's in other quadrants, but the only quadrant that makes any sense, because you know life is in quadrant 1, is we're looking when what's happening in quadrant 1. And it really doesn't even matter after 6, because if this problem went up even more, it doesn't make any difference, because once the volume is 0, it's not going to help. If it's 7, 8, 9, it's not going to work. All right. So we're going to try 2 and 6 to see if by looking at this, if we were right in our assumption. So we're going to go back to our factored form. So the factored form we're going to use is right here, because the 12 doesn't really matter anymore. And if I did to the left of 2, we'll say 1. This would be negative. This would be negative. Negative times a negative is positive. If we did something between 2 and 6, let's pick a number, we'll say 3. This would be positive, this would be negative, so this is going to be negative. Something greater than 6, this would be positive here, and this would also be positive. So as you see here, right here, this is our max, this is our min, and so we are right. It looks like x equal 2 to cut the corners out, and we're talking, does it say inches or does it say any kind of unit? Yep, inches. So x is going to be 2 inches. I just had to look at the problem one more time. So that's our answer on this one. Again, just to kind of go over this, you do not need to have a constraint because we already labeled the picture with the constraint of the folded box.